The universe is changing. Why everyone should know about dark energy. The Big Bang Theory represents the cornerstone of modern cosmology, explaining the origin and evolution of our universe. This fundamental theory asserts that approximately 13.8 billion years ago, all matter and energy in the universe were concentrated in an unimaginably dense and hot point, known as the cosmological singularity. But the path to this understanding was long and winding, beginning with simple astronomical observations in the early 20th century. The development of this theory began in the 1920s with Edwin Hubble's observations, who discovered that distant galaxies are moving away from us at velocities proportional to their distance. This phenomenon, known as Hubble's law, first indicated that the universe is expanding. The logical consequence of this discovery was revolutionary. If the universe is expanding today, then in the past it was smaller, denser, and hotter. This simple idea quickly received theoretical foundation. The first theoretical foundations were laid in the 1920s by Russian physicist Alexander Friedmann and Belgian priest Georges Lemaitre, who independently found solutions to Einstein's equations describing an expanding universe. Lemaitre was the first to propose the idea of the primeval atom from which the entire universe arose. Interestingly, the term Big Bang was coined by British astronomer Fred Hoyle in 1949 during a BBC radio broadcast, and he used it in a somewhat derogatory tone since he was a proponent of the alternative steady-state theory of the universe. Visual representation of the cosmic microwave background radiation across different epochs of the universe's history with redshift and distance scale. However, for the theory to become widely accepted, convincing observational evidence beyond simple cosmic expansion was required. The most convincing proof of the Big Bang Theory came with the discovery of the cosmic microwave background radiation, CMB, in 1965 by American radio astronomers Arno Penzias and Robert Wilson at Bell Labs. Working with the sensitive Holmdel horn antenna, originally designed for satellite communications, they detected persistent radio noise that wouldn't disappear regardless of observation direction or time of day. This mysterious signal was initially even attributed to pigeon droppings from birds nesting in the antenna. But the true nature of this radiation turned out to be much more fundamental. The mysterious signal proved to be relic radiation, remnants of that primordial light that could freely propagate through the universe after it cooled sufficiently for neutral atoms to form approximately 380,000 years after the Big Bang. The temperature of this radiation is 2.725 Kelvin, which is extraordinarily close to theoretical predictions. The significance of this discovery cannot be overstated, as it connected observable reality with theoretical predictions in an incredibly precise manner. The CMB represents a kind of photograph of the infant universe, taken at the moment it became transparent to light. Moreover, tiny temperature fluctuations in this radiation, first detected by the COBE satellite in the 1990s and measured in detail by the WMAP and Planck satellites, are imprints of those primordial quantum fluctuations that subsequently grew into galaxies, stars, and all large-scale structures of the universe. The precision of these measurements is mind-boggling. The Ferris experiment on the COBE satellite showed that the CMB spectrum corresponds to black body radiation with incredible accuracy. This correspondence is so precise that measurement errors cannot be distinguished on the graph. They are hidden under the theoretical curve. No alternative theory predicts such a precise black-body spectrum for the universe's background radiation, making this discovery practically definitive proof of the Big Bang theory. If the cosmic microwave radiation showed us a photograph of the early universe, then the second fundamental proof of the Big Bang theory relates to its chemical composition, the observed ratios of light elements in the universe. The theory predicts that in the first minutes after the Big Bang, when the temperature was high enough for nuclear reactions but low enough for nuclear stability, primordial nucleosynthesis should have occurred. This process should have led to a strictly determined result: the formation of approximately 75% hydrogen and 25% helium by mass, along with trace amounts of deuterium, helium-3, and lithium-7. Critically important is that these proportions could not be arbitrary. They were rigidly determined by nuclear reaction physics and cosmological parameters of the early universe. And once again, theory was brilliantly confirmed by observations. Observations show that exactly such ratios are seen in the most ancient objects of the universe, where subsequent stellar nucleosynthesis has not yet significantly altered the original composition. This agreement between theory and observations is particularly impressive, considering the complexity of nuclear processes and the precision of required cosmological parameters. The logical development of Hubble's original observations became modern precision measurements of universe expansion. The third key evidence is the observed expansion of the universe itself, but now studied with unprecedented accuracy. Modern measurements using various methods, including observations of type Ia supernovae, Cepheid variable stars, and gravitational lensing, not only confirm that distant galaxies are indeed moving away from us at velocities proportional to their distance, but also reveal new aspects of cosmic evolution. The most unexpected discovery was that this expansion is accelerating, a discovery for which the 1998 Nobel Prize in Physics was awarded. This acceleration is attributed to mysterious dark energy, comprising about 68% of all energy in the universe. Thus, studying universe expansion not only confirmed the basic predictions of Big Bang theory, but also opened new horizons for understanding the fundamental nature of the cosmos. Paradoxically, the very success of Big Bang theory has generated new fundamental problems. Despite the enormous success of the theory, modern observations have revealed several problems requiring further study. One of the most significant is the so-called Hubble problem. The discrepancy in measurements of the Hubble constant by different methods. Measurements based on observations of nearby objects give a value of about 73 kilometers per second per megaparsec, while measurements based on the CMB give a value of about 67 kilometers per second per megaparsec. This discrepancy may indicate the need to revise some aspects of the standard cosmological model or the existence of new physics. Some researchers suggest that our galaxy may be located in a huge cosmic void, affecting local measurements of expansion velocity. Alternatively, This could be a sign that our understanding of dark energy or other universe components needs substantial revision. The influence of Big Bang theory extends far beyond pure science. Big Bang theory has radically changed our understanding of the universe and our place in it. It showed that the universe has a history. It evolves from simpler to more complex states. This discovery raised fundamental questions about the nature of time, space, and causality that continue to influence philosophy and theology. The theory also predicts the existence of a cosmological horizon, the limit of the observable universe beyond which we cannot principally obtain information. The size of the observable universe is about 46 billion light-years in radius, which is larger than the universe's age in light-years due to space expansion. This means that most of the universe will forever remain inaccessible to us. Modern research continues to develop and refine our understanding of the early universe. Current research using the James Webb Space Telescope is already beginning to reveal unexpected features of the early universe, showing that the formation of the first galaxies occurred faster and more efficiently than models predicted. These observations do not refute Big Bang theory, but require refinement of our understanding of structure formation processes in the early universe, demonstrating that even established theories continue to evolve under the influence of new data. The first moments, from Planck time to inflation. If Big Bang theory explains the general picture of universe origin, then the earliest moments of its existence represent one of the most fascinating and mysterious areas of modern physics. This epoch, spanning from the very moment of the Big Bang to the completion of cosmic inflation, determined all fundamental properties of our cosmos and created conditions for all subsequent development. The Planck epoch, at the boundaries of the knowable. Our journey into the past begins with the Planck epoch. The time from 0 to time equals 10 to the minus 43 seconds after the Big Bang, named after Max Planck, who introduced the quantum of action, a fundamental constant of quantum mechanics. This period represents the absolute limit of our knowledge about the early universe, since this is precisely where our modern physical theories cease to work. During the Planck epoch, the universe existed in a state that is difficult even to imagine. It was so small, hot, and dense that familiar concepts of space and time lose meaning. The universe's size was on the order of the Planck length, 10 to the minus 35 meters. Temperature reached 10 to the 32 Kelvin, and energy density was colossal, 10 to the 113 joules per cubic meter. For comparison, this means that the entire universe observable today was compressed into a volume smaller than an atom. Timeline of the universe's history from the Big Bang through early epochs to present with key cosmic events and particle formation. In these extreme conditions, something fundamental to understanding the nature of reality occurred. All four fundamental interactions, gravitational, electromagnetic, strong and weak electromagnetic, weak and strong nuclear, were unified into a single force. Quantum effects of gravity became dominant, and Einstein's classical general relativity ceased to be applicable. This unification of forces represented a state of symmetry that was subsequently broken, leading to the diversity of physical phenomena we observe today. According to some theoretical models, during the Planck epoch, space-time represented a quantum foam, a turbulent structure where virtual black holes constantly appeared and disappeared. The sizes of these fluctuations were on the order of Planck length, and their existence time, Planck time. This picture radically differs from our ordinary understanding of space as a smooth continuum. Understanding the Planck epoch encounters a fundamental problem of modern physics. Describing it requires a theory of quantum gravity, a unification of quantum mechanics and general relativity. Despite decades of intensive research, no such complete theory yet exists. This creates a unique situation in science where we know what should happen physically, but lack the mathematical apparatus for precise description of these processes. Existing approaches, such as string theory and loop quantum gravity, offer different scenarios, but none has received definitive experimental confirmation. String theory suggests that during the Planck epoch, the universe could have had up to 10 or 11 dimensions, most of which were compactified to microscopic sizes. Loop quantum gravity, on the other hand, proposes a discrete structure of space-time at Planck scales, where space consists of the tiniest atoms of geometry. As the universe expanded and cooled, a process of successive symmetry breaking began that determined the structure of the modern world. After the Planck epoch, in the interval from 10 to the minus 43 to 10 to the minus 36 seconds, came the Grand Unification Epoch, GUT. During this period, temperature decreased to 10 to the 28th Kelvin, allowing gravity to separate from the remaining interactions, which still remained unified. This separation was not merely an academic moment. It had profound consequences for the universe's future. Grand unification theories predict the existence of superheavy particles with masses on the order of 10 to the 16th giga-electron volts. This is 1 trillion times greater than proton mass. These particles could play a key role in determining fundamental properties of the universe, including baryon asymmetry, the predominance of matter over antimatter that we observe today. Processes during the GUT epoch could also create topological defects, cosmic strings, domain walls, and monopoles. These exotic objects represent scars from phase transitions in the early universe and, if they exist, should have observable effects on cosmology. The most dramatic event of the early universe was cosmic inflation, a period of exponential expansion believed to have occurred between 10 to the power of minus 36 and 10 to the minus 32 seconds after the Big Bang. During this unimaginably short period, much less than the time it takes light to travel from one end of an atom to the other, the universe increased in size by at least 10 to the 26th power times, and possibly much more. Timeline of the early universe from inflation to the present, showing key cosmic milestones like CMB, last scattering and first star formation with density and polarization, signals of the cosmic microwave background. To understand the scale of this expansion, imagine a grain of sand instantly growing to the size of the visible universe. And this is still a conservative estimate of inflationary expansion. Such extreme expansion seems impossible, but it elegantly solves several fundamental problems that would otherwise make Big Bang theory internally contradictory. Inflation theory was developed in the late 1970s and early 1980s by physicists such as Alexei Starobinsky, Alan Guth, and Andrei Linde. It arose as an attempt to solve serious conceptual problems of the standard Big Bang model that threatened the very viability of the theory. The first of these problems, the horizon problem, consisted of an apparent paradox. Regions of the universe that were never in causal contact with each other. I.e., light didn't have time to travel between them during the universe's existence, nevertheless have practically identical temperatures. How did they agree to have identical properties? Inflation solves this problem by assuming that all regions observable today were in causal contact before inflation began, then were stretched to enormous scales. The closely related flatness problem concerned the geometry of universe space. Observations show that the universe's space geometry is very close to Euclidean. This requires incredibly precise fine-tuning of initial conditions in the standard model. Deviation from critical density by 1 part in 10 to the 60 in early times would have led to a radically different universe. Inflation naturally leads to flat geometry since any initial curvature is stretched by inflationary expansion to invisibility. The third relic problem was more technical but no less important. Grand unification theories predict the formation of exotic particles such as magnetic monopoles, which should be observed today in large quantities if there were no mechanism for their dilution. Inflation dilutes these relics to invisibility, explaining why we don't see them. But what is the mechanism of this amazing process? The driving force of inflation is a hypothetical scalar field called the inflaton. This field has an unusual property. Its energy creates negative pressure, which within general relativity leads to accelerated space expansion. This seems paradoxical from everyday experience, but such behavior is precisely a consequence of Einstein's equations. During inflation, the inflaton field was in a state of false vacuum, a metastable state with high energy, like a ball balancing on a hilltop. The slow rolling of the field toward the true potential minimum, like a ball slowly rolling down a hill, provided exponential expansion. It's important to understand that this was not ordinary movement through space, but a change in the field itself that permeated all space. Perhaps the most striking consequence of inflation is the transformation of microscopic quantum fluctuations into macroscopic universe structures. The most important consequence of inflation is the generation of primordial density fluctuations. Quantum fluctuations of the inflaton field, stretched by inflation to cosmological scales, became the seeds of all future structures, galaxies, stars, and planets. Thus, quantum mechanics, acting at subatomic scales, determined the large-scale structure of the entire universe. This process can be represented as follows. Tiny quantum ripples in the inflaton field, smaller than a proton, were stretched by inflation to sizes comparable to galaxies and galaxy clusters. Where the field was slightly denser, galaxies later formed. Where it was more rarefied, cosmic voids formed. Inflation could not continue forever, at least in our part of the universe. Inflation ended when the inflaton field reached the minimum of its potential. At this moment, all the enormous potential energy of the field was released as ordinary particles and radiation, a process called reheating. This was the moment when the universe transitioned from the exotic inflationary state to the more familiar hot plasma of elementary particles. Temperature after reheating could reach 10 to the 28th Kelvin, corresponding to energies of 10 to the 15th giga-electron volts. This created a hot plasma of elementary particles that became the basis for all subsequent stages of universe evolution. Essentially, this moment can be considered the true beginning of ordinary cosmological history, since from this point, the universe evolved according to well-understood physical laws. Inflation theory not only solved conceptual problems, it made specific, testable predictions. Inflation theory makes several concrete predictions, many of which are confirmed by observations. The density fluctuation spectrum should be nearly scale invariant, identical at all scales, with a small deviation characterized by the spectral index. Planck satellite measurements give a spectral index value of n equals 0.968 plus or minus 0.006, which excellently agrees with the simplest inflation models. Inflation also predicts the existence of primordial gravitational waves, imprints of inflationary expansion in cosmic microwave radiation polarization. The search for these signals represents one of the main tasks of modern observational cosmology. Their detection would be direct proof that inflation actually occurred and would allow studying physics at energies unattainable in terrestrial accelerators. However, the triumph of inflation breeds new questions. Despite inflation theory's successes, it is not without problems. The nature of the inflaton field remains mysterious. No known particle fits this role. Moreover, inflation apparently should lead to eternal expansion in most regions, creating an infinite multitude of pocket universes, a multiverse. This raises deep questions about the nature of physical laws and observability in cosmology. Recent research proposes alternative mechanisms based on modified gravity or the role of gravitational waves in forming primordial perturbations. These ideas are still in development, but they show that our understanding of the earliest moments of universe history continues to evolve. Perhaps future observations will show that inflation is only part of a more complex picture of cosmic origin. The birth of the first elements. After inflation completed and established the basic physical conditions of the universe, the next critical phase of its evolution began. Primordial nucleosynthesis represents one of the most well-understood and precisely tested aspects of Big Bang theory. This process, occurring in the first 20 minutes of the universe's existence, determined the chemical composition of the cosmos for billions of years ahead, and created the foundation for the formation of the first stars and galaxies. After inflation completed and subsequent reheating, the universe represented a hot plasma of elementary particles, quarks, leptons, photons, and other exotic particles. But as expansion and cooling continued, this primordial energy gradually condensed into more familiar forms of matter. By the time the universe's age reached about 1 second, temperature had dropped to approximately 1 billion Kelvin, still high enough for nuclear reactions, but low enough for stable atomic nuclei to exist. Illustration of primordial nucleosynthesis, showing the progression from quarks and leptons to the formation of hydrogen and helium atoms in the early universe. This temperature proved to be a critical threshold in universe history. At higher temperatures, energetic photons destroyed any atomic nuclei immediately after their formation. At lower temperatures, the kinetic energy of protons and neutrons became insufficient to overcome the Coulomb barrier and carry out nuclear reactions. Thus, there existed a narrow window of opportunity for primordial nucleosynthesis, which determined its unique role in cosmological history. At this decisive moment, the universe contained approximately equal amounts of protons and neutrons, but their ratio slowly changed due to weak interactions. Neutrons could transform into protons and vice versa through reactions with neutrinos and positrons. However, since the neutron is slightly heavier than the proton by 1.3 mega-electron volts, equilibrium gradually shifted in favor of protons. This seemingly insignificant mass imbalance had a fundamental influence on the chemical composition of the entire universe. As the universe continued cooling, it approached a moment that could be called the chemical fate of the cosmos. By the beginning of nucleosynthesis, approximately 3 minutes after the Big Bang, the ratio of neutrons to protons was about 1:7. This ratio became a critical factor determining the final proportions of light elements. But before these nucleons could combine into heavier nuclei, they encountered a fundamental obstacle. The key limitation of primordial nucleosynthesis was what is called the deuterium bottleneck. Deuterium, heavy hydrogen, consisting of 1 proton and 1 neutron, is an intermediate product in the formation of heavier elements, a kind of bridge between simple nucleons and complex nuclei. However, deuterium is rather weakly bound. Its nuclear binding energy is only 2.2 mega-electron volts. This relative weakness created a critical problem. At high temperatures exceeding 100 million Kelvin, energetic photons easily destroyed deuterium nuclei immediately after their formation. The process resembled trying to build a house from ice cubes under the scorching sun. As soon as the building material appeared, it immediately melted. Only when temperature fell below this critical threshold could deuterium accumulate in significant quantities, opening the path for synthesis of heavier elements. This moment can be considered the beginning of the universe's true nuclear era. Once the deuterium bottleneck was overcome, the universe entered a period of intensive nuclear synthesis. As soon as temperature became low enough for stable deuterium existence, a rapid cascade of nuclear reactions began that within minutes created the foundations of modern cosmic chemical composition. The main reactions of primordial nucleosynthesis represented an elegant sequence of processes. Deuterium formation, the first step toward complexity. Helium-3 synthesis, development toward stability. Tritium formation, alternative pathway. Helium-4 synthesis, achieving stability. Lithium-7 formation, limit of possibilities. Each of these reactions was not a random event, but a natural consequence of fundamental properties of atomic nuclei and conditions in the early universe. The most important of these reactions was helium-4 formation, since this nucleus is exceptionally stable due to its magic configuration of 2 protons and 2 neutrons. This stability meant that practically all free neutrons were ultimately incorporated into helium-4 nuclei. The result of primordial nucleosynthesis was not random. It was rigidly determined by initial conditions and fundamental constants of nature. Since the initial ratio of neutrons to protons was 1:7, and each helium-4 nucleus contains 2 neutrons, simple arithmetic shows that about 25% of all baryonic mass in the universe was converted to helium-4. The remaining 75% remained as hydrogen, protons. This proportion proved remarkably stable and is reproduced in all regions of the universe where stellar evolution has not yet significantly altered the original composition. Deuterium, helium-3, and lithium-7 formed in much smaller quantities, at the level of parts per million or billion relative to hydrogen. This occurred because nucleosynthesis quickly ceased when temperature and density fell below threshold values for nuclear reactions. Universe expansion acted as a natural switch, stopping nuclear processes at a precisely determined moment. Critically important is that elements heavier than lithium practically did not form during primordial nucleosynthesis. This limitation is connected to the absence of stable nuclei with mass numbers 5 and 8, the so-called stability gap. To overcome this gap and synthesize carbon and heavier elements requires much more extreme conditions that are realized only in stellar interiors. Thus, primordial nucleosynthesis created a chemically simple but stable foundation for future evolution. One of the most remarkable aspects of primordial nucleosynthesis is its extreme sensitivity to cosmological parameters. The yield of primordial nucleosynthesis is extremely sensitive to cosmological parameters, especially the density of baryons ordinary matter in the universe. The ratio of baryons to photons, approximately 10 to the -9, is a critical parameter determining nuclear reaction efficiency. This dependence creates a powerful tool for cosmology. At higher baryon density, nucleosynthesis would be more efficient, leading to a greater fraction of helium and smaller fraction of deuterium. At lower density, the opposite. Observed proportions of light elements allow very precise determination of baryonic matter density in the universe. Thus, by studying the chemical composition of ancient stars, astronomers can weigh all baryonic matter in the cosmos. When theoretical predictions of primordial nucleosynthesis were first formulated, they represented a bold extrapolation of physical laws to extreme conditions of the early universe. Therefore, agreement between theory and observations proved particularly impressive. Predictions of primordial nucleosynthesis are brilliantly confirmed by observations. Helium-4 content in the most ancient and chemically simple stars is about 24 to 25% by mass, which precisely corresponds to theoretical predictions. This agreement is especially impressive considering that stellar nucleosynthesis practically does not produce helium-4 in significant quantities. Deuterium presents an even more stringent test of theory since stars only destroy it without creating it. Deuterium is observed in the interstellar medium and in atmospheres of some planets with content of about 2 to 3 parts per 100,000 relative to hydrogen. This also agrees well with predictions, especially considering that any deviation should occur only in the direction of decrease. However, not all elements give such perfect agreement. Lithium-7 presents a more complex picture and remains the source of one of cosmology's unsolved problems. Observed lithium content in old stars is approximately 2 to 3 times less than predicted by primordial nucleosynthesis. This lithium problem remains one of modern cosmology's unsolved mysteries and may indicate incompleteness in our understanding of either nucleosynthesis or stellar evolution. Primordial nucleosynthesis did not occur in isolation. It was closely connected with other fundamental processes in the early universe. Neutrinos played an important role in primordial nucleosynthesis. These nearly elusive particles that weakly interact with matter but exist in enormous quantities. Neutrinos influence the universe's expansion rate and the equilibrium between protons and neutrons. The number of neutrino types, flavors, directly affects helium-4 yield. This influence occurred through changes in universe expansion rate. More neutrino types meant faster expansion, which shortened the time available for nuclear reactions. Observed proportions of light elements allow constraining the number of neutrino types. Results agree with the existence of 3 neutrino types, confirmed by particle physics experiments. This represents a remarkable example of how cosmological observations can test fundamental physics. The results of primordial nucleosynthesis had far-reaching consequences for all subsequent universe evolution. The chemical composition established by primordial nucleosynthesis determined the character of first star formation. Since elements heavier than helium were practically absent, the first stars, population 3, could not use heavy elements for cooling gas clouds and could rely only on molecular hydrogen. This led to the formation of very massive stars, radically different from modern ones. Initial deuterium content also continues to influence processes in the modern universe. Deuterium is an important nuclide for thermonuclear reactions and can serve as an indicator of cosmological history in observations of distant quasars. Studying its distribution in various cosmological epochs helps trace chemical composition evolution from the earliest times to our days. The study of primordial nucleosynthesis continues to develop using increasingly precise methods and new approaches. Modern research on primordial nucleosynthesis focuses on refining nuclear reaction constants, searching for new lithium formation mechanisms, and studying the influence of exotic particles on the process. New ground-based experiments measure nuclear reaction cross-sections at low energies corresponding to early cosmic conditions. Future cosmological surveys, such as Euclid and LSST, will allow more precise measurement of light element content in various cosmological epochs, helping better understand both primordial nucleosynthesis and subsequent chemical evolution of the universe. These studies may also shed light on the nature of dark matter and other exotic cosmic components that could have influenced processes in the early universe. The Dark Ages and First Stars. After primordial nucleosynthesis determined the basic chemical composition of the universe, the cosmos entered a period that radically differed from all previous and subsequent epochs. The Dark Ages represent one of the most mysterious and poorly studied periods in universe history. This period, lasting from recombination approximately 380,000 years after the Big Bang to the ignition of first stars several hundred million years later, was a time of cardinal changes in cosmic structure and composition. To understand the significance of the Dark Ages, one must first realize the drama of the transition that preceded them. Before the recombination epoch, the universe represented hot plasma of free protons, electrons, and helium nuclei at a temperature of about 4,000 Kelvin. Under these conditions, photons constantly scattered off free electrons, making the universe opaque to light, like dense fog hiding the surrounding landscape. But as the universe expanded and cooled, an event occurred that can be called the Great Enlightenment. When temperature dropped to approximately 3,000 Kelvin, protons and electrons could combine into neutral hydrogen atoms, and helium nuclei captured electrons, forming neutral helium. This process, called recombination, though it was actually the first combination, occurred quite rapidly by cosmological standards, over several tens of thousands of years. The result of this process was truly revolutionary. With the formation of neutral atoms, the universe suddenly became transparent to radiation. Photons that previously constantly interacted with charged particles could now freely propagate through space. These last photons we observe today as cosmic microwave background radiation. Thus, recombination not only changed the physical state of the universe, but also created an observational snapshot of this critical moment in cosmic history. After this dramatic transition, the universe plunged into a period that astronomers figuratively call the Dark Ages, or Dark Epoch. After recombination, the universe entered a period astronomers call the Dark Ages, or Dark Epoch. This period was characterized by several key features that made it unique in cosmic history. First and foremost, it was a time of complete absence of light sources. No stars, quasars, or other bright objects existed. The only sources of photons were residual radiation from recombination and rare photons emitted by neutral hydrogen during transitions between hyperfine structure levels, 21 centimeter line. The universe was literally dark in the most direct sense of the word. Simultaneously, constant cooling occurred. Gas temperature steadily decreased as the universe expanded, dropping from 3000 Kelvin to approximately 60 Kelvin by the end of the Dark Ages. This cooling was not merely a side effect of expansion, it created conditions for future structure formation processes. Chemically, the universe remained surprisingly simple. Simple chemical composition determined all physical processes. The cosmos consisted almost exclusively of hydrogen, 75%, and helium, 25%, with negligible traces of lithium and deuterium. Heavy elements necessary for dust and planet formation did not exist. This chemical simplicity meant that physical processes were limited to interactions of only a few atomic types. But most importantly, dark matter gained freedom of action. In the absence of radiation pressure, dark matter could freely collapse under gravity, forming the first large-scale structures. This became the key process that set the stage for all subsequent events. Despite its name, the Dark Epoch was a period of intensive, though invisible, activity. Although the epoch is called dark, it was a period of intense structure formation. Small density fluctuations that arose during inflation and were imprinted in cosmic microwave radiation served as seeds for structure growth. These fluctuations, comprising only a few parts per 100,000, became the foundation for all future universe complexity. Dark matter, comprising about 85% of all matter in the universe, began collapsing into gravitationally bound structures, dark matter halos. The process followed a hierarchical principle. First, small halos formed, which then merged into larger formations. This process can be imagined as building an invisible framework for future galaxies and galaxy clusters. Ordinary baryonic matter initially could not effectively participate in this process due to gas pressure that prevented gravitational collapse. However, over time, gravitational attraction of dark matter halos began slowly drawing gas inward, creating conditions for future star formation. This process was gradual but relentless, and it prepared the material foundation for the appearance of first stars. Studying the Dark Ages presents unique observational challenges since this period left virtually no direct traces in modern observations. The only way to study the Dark Ages is through observation of 21-centimeter radiation from neutral hydrogen. This spectral line arises from transitions between two hyperfine levels of hydrogen's ground state. Although this transition is extremely rare for individual atoms, occurring on average once per 11 million years, the enormous quantity of hydrogen atoms in the universe makes this signal potentially observable. The intensity of this radiation depends on gas temperature and density, as well as atomic excitation conditions. Since the universe expands, this radiation's wavelength is stretched, redshifted, allowing us in principle to observe various epochs in universe history. Regions with higher gas density should give stronger signals, creating a kind of map of matter distribution during the Dark Ages. Modern radio telescopes attempt to register the global 21-centimeter radiation signal from the Dark Ages, which would be a revolutionary breakthrough in studying this period. However, These observations are extremely difficult due to signal weakness and powerful interference from terrestrial sources. The signal from the Dark Ages is millions of times weaker than interference from FM radio stations and other sources, making its detection one of modern astronomy's most challenging tasks. Modern research is beginning to reveal unexpected aspects of the Dark Ages that force reconsideration of our understanding of this period. Recent studies have shown that the Dark Ages may not have been as cold as previously assumed. Observations and theoretical models indicate that intergalactic gas could have been significantly warmer than expected even before first star formation. This discovery has profound implications for our understanding of Dark Ages physics. This discovery forces reconsideration of our Dark Ages understanding. Possible sources of additional heating include dark matter annihilation, exotic particle decay, or other currently unknown processes. Such heating could significantly affect first star and galaxy formation processes, changing gas collapse conditions and first-generation star characteristics. The Dark Ages could not last forever. Gradually, in the centers of the most massive dark matter halos, conditions became suitable for gravitational gas collapse and first star formation. The end of the Dark Ages was marked by the formation of first stars, known as population 3 stars. These objects radically differed from modern stars and represented a genuine revolution in cosmic evolution. First and foremost, the first stars were gigantic monsters. Their masses ranged from 30 to 300 solar masses, and possibly more. Such large masses were a consequence of the absence of heavy elements that in modern stars promote gas cloud cooling and fragmentation into smaller parts. In the primordial environment, molecular hydrogen was the only effective coolant, limiting fragmentation possibilities. The chemical virginity of these stars was absolute. They consisted practically only of hydrogen and helium, making them unique objects in the universe. This compositional simplicity radically affected their internal structure and evolution. Due to enormous masses, these stars had very short lives, only a few million years compared to billions of years for sun-like stars. They burned their nuclear fuel at incredible rates, making their evolution rapid. But most importantly, they were incredibly bright, millions of times brighter than the sun, capable of ionizing hydrogen at enormous distances. This brightness meant that even a relatively small number of such stars could have global impact on intergalactic medium conditions. First star formation represented a complex physical process occurring in a chemically simple but dynamically complex environment. First star formation occurred in centers of dark matter halos with masses around 1 million solar masses. Gas slowly fell into these gravitational wells, gradually heating during compression. This process was much slower and more complex than modern star formation due to limited cooling possibilities. Hydrogen molecules, H2, played a key role in gas cooling. In the absence of dust and heavy elements, molecular hydrogen was the only effective coolant, allowing gas to compress to densities necessary for igniting nuclear reactions. Formation of these molecules was itself a complex process requiring specific density and temperature conditions. Computer simulations show that first star formation was turbulent and complex. Gas formed accretion disks, experienced fragmentation, and created complex flow structures. Surprisingly, such complex hydrodynamic structures could arise in a chemically simple environment. The appearance of first stars marked the end of simplicity and beginning of complexity in the universe. First stars had revolutionary impact on the universe, consequences of which are felt to this day. First and foremost, they became the first chemical factories of the cosmos. In their cores, elements heavier than lithium were synthesized for the first time in the universe: carbon, oxygen, silicon, iron, and others. These elements became building material for future generations of stars, planets, and ultimately, life. Simultaneously, reionization of intergalactic medium began. Powerful ultraviolet radiation from these stars began reionizing neutral hydrogen, launching the reionization epoch. This process radically changed physical conditions in intergalactic space and affected subsequent structure formation. Mechanical feedback from first stars was also significant. Stellar winds and supernova explosions scattered synthesized elements through intergalactic space and influenced formation of next-generation stars. These processes created complex feedback systems that regulated star formation rates in the early universe. Finally, the most massive population 3 stars collapsed into black holes, becoming seeds for supermassive black holes in galaxy centers. These primordial black holes play key roles in modern astrophysics and cosmology. From darkness to light, cosmic dawn. The period of first star ignition is justly called cosmic dawn. This was the moment when the universe first illuminated itself from within after a long period of darkness. This process was gradual, spreading from the densest regions to less dense ones over several 100 million years. Cosmic dawn was not an instantaneous event, but represented a time-extended process of gradual switching on the lights in the universe. Modern telescopes, especially the James Webb Space Telescope, are beginning to discover galaxies from the cosmic dawn epoch. These observations show that structure formation in the early universe occurred faster and more efficiently than theoretical models predicted. Some discovered galaxies proved unexpectedly massive and bright for their age, forcing reconsideration of early star formation models. Transition to new era. Beginning of reionization. First star formation marked not only the end of the Dark Ages, but also the beginning of a new cosmological epoch. First star formation marked the end of the Dark Ages and beginning of the reionization epoch. This transition was not instantaneous, but represented an extended process completed approximately 1 billion years after the Big Bang. The reionization epoch represents the last major phase transition in universe history, when intergalactic medium definitively transitioned from neutral to ionized state. This opened the path for formation of modern galaxy and star types, including stars like our Sun. Thus, the Dark Ages and subsequent first star formation represent a critical bridge between the simple early universe and complex modern cosmos we observe today. Alternative theories and models. As the standard model of cosmology achieved impressive successes in explaining observed universe properties, the scientific community simultaneously developed alternative approaches to understanding cosmic origin and evolution. Despite impressive successes of the standard cosmological model based on Big Bang theory, alternative approaches to understanding universe origin and evolution continue to develop in the scientific community. These theories arise as attempts to solve unresolved problems of the standard model or propose fundamentally new views on cosmic nature. Their existence does not mean the main theory's inadequacy, but rather reflects science's healthy skepticism and constant search for deeper understanding. One of the most philosophically attractive alternatives is the concept of a cyclical universe, which offers a radically different view of cosmic time. One of the most intriguing alternatives is the cyclical universe model, suggesting that the cosmos undergoes infinite cycles of expansion and contraction. This idea has ancient roots in philosophy and religion, but modern versions are based on rigorous physics and cosmology, representing an attempt to solve some fundamental problems of the standard model. Historically, the first scientific cyclical model was proposed by Richard Tolman in the 1930s. It assumed that the universe expands to maximum size, then collapses back into a big crunch, after which the cycle repeats. This elegant idea eliminated the need to explain the beginning of time, but encountered a serious physical problem. Entropy in the universe should accumulate from cycle to cycle, ultimately leading to cosmic thermal death. The solution to this fundamental problem came only in the early 2000s, when Paul Steinhardt and Neil Turok proposed a radically new version of the cyclical model. In the early 2000s, Paul Steinhardt and Neil Turok proposed a new version of the cyclical model based on string theory and extra dimensions. In their model, our four-dimensional universe exists on one of two parallel branes in five-dimensional space, representing a completely new way of thinking about reality's structure. In this exotic picture, periodic brane collisions lead to events we perceive as Big Bangs. After each collision, branes repel each other, the universe expands and cools, structures form. Then slow contraction begins, leading to new collision. The key advantage of this model is that it solves the entropy problem. Each cycle includes a period of accelerated expansion that stretches and dilutes entropy, black holes, and other products of the previous cycle. A particularly interesting element of modern cyclical models is the ekpyrotic phase, which offers an alternative to cosmic inflation. An important element of modern cyclical models is the ekpyrotic phase, a period of very slow contraction before each bounce. During this phase, quantum fluctuations generate a nearly scale-invariant spectrum of density perturbations that explains observed cosmic microwave radiation structure without requiring inflationary expansion. Critically important is that ekpyrotic models predict a somewhat different spectrum of primordial gravitational waves compared to inflationary models, making them potentially distinguishable through future observations. If future gravitational wave detectors discover signals corresponding to ekpyrotic predictions, this would be decisive evidence for cyclical cosmology. Parallel development of quantum gravity theories open new possibilities for alternative cosmological models. Development of quantum gravity theories led to models with quantum bounce that avoid cosmological singularities. Within loop quantum gravity, for example, it's assumed that at Planck scales, space-time has discrete structure that prevents infinite matter compression. In such models, the classical Big Bang is replaced by a big bounce, a smooth transition from contraction phase to expansion phase without mathematical singularity. This opens possibilities for pre-Bang universe phase existence and may radically change our understanding of cosmic origin. Quantum gravity thus not only solves technical problems, but also opens new conceptual horizons. Another direction of alternative theories became the idea that nature's laws themselves may evolve. Some alternative theories suggest that fundamental nature constants, such as light speed, gravitational constant, or Planck's constant, may vary with time. Such variations could radically change our understanding of cosmological evolution and offer new solutions to old problems. Models with variable constants may solve some standard cosmology problems without introducing exotic energy forms. For example, changing the gravitational constant may explain observed universe expansion acceleration without dark energy. These theories are particularly attractive because they offer testable predictions about how physical laws should have behaved in different cosmological epochs. Perhaps the most radical challenge to the standard model comes from theories proposing to change our understanding of gravity itself. Another class of alternative theories suggests that gravity itself behaves differently than general relativity predicts, especially at cosmological scales. These theories arose partly as responses to dark matter and dark energy problems. Modified Newtonian dynamics, MOND, represents one of the most studied examples of such theories. MOND suggests that Newton's law of gravitation is modified at very small accelerations. This theory was developed to explain galaxy rotation curves without invoking dark matter. Relativistic MOND versions, such as tensor vector scalar gravity, TVS, attempt to create a full alternative to general relativity. Although MOND successfully explains many observations at galactic scales, it encounters difficulties explaining cosmological phenomena such as large-scale structure formation and acoustic peaks in cosmic microwave radiation spectrum. This creates an interesting situation where theory works at some scales, but needs refinement at others. Development of these ideas led to creation of even more general modified gravity theories. F of R gravity theories replace linear dependence on scalar curvature R in Einstein's equations with a more general function f of r. These theories can lead to late-time accelerated expansion without dark energy, making them an attractive alternative to the standard model. More exotic modifications also exist, including additional scalar or vector fields, higher curvature derivatives, or extra spatial dimensions. Each of these theories offers its own view of gravity nature and cosmological evolution. An interesting example of alternative theory evolution is the fate of the steady-state universe model. Historically important alternative to Big Bang theory was the steady-state model proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi in the 1940s. This model assumed the universe always looked roughly the same, with continuous creation of new matter to compensate for dilution during expansion. The classical steady-state model was convincingly refuted by cosmic microwave radiation discovery, which clearly indicated a hot universe past. However, some modern theories revive steady-state cosmology elements in new forms, for example, in models with continuous dark energy creation. These new versions attempt to preserve attractive steady-state model aspects while avoiding its observational problems. A completely different approach is represented by plasma cosmology, which emphasizes electromagnetic processes' role. Plasma cosmology, developed by Hannes Alf Venn and his followers, suggests that electromagnetic forces play a dominant role in large-scale universe structure. This theory emphasizes plasma processes and magnetic fields' importance in cosmological phenomena, contrasting with the standard approach where gravity dominates. Although plasma cosmology explains some observations and correctly predicts magnetic fields' importance in astrophysics, it cannot reproduce the precise cosmic microwave radiation spectrum or explain light element nucleosynthesis without additional assumptions. Nevertheless, it made important contributions to understanding plasma processes' role in space. One of the most philosophically provocative ideas in modern cosmology is the multiverse concept. The multiverse concept suggests existence of multiple universes with different physical laws and constants. This idea arose as a possible solution to fundamental constants' fine-tuning problem, but has deep implications for understanding reality's nature. Several different multiverse types exist, each with its own features. Patchwork multiverse is based on the idea that in an infinite universe, statistical fluctuations lead to regions with any possible initial conditions. Somewhere, an exact copy of our universe region might exist. Inflationary multiverse is a consequence of eternal inflation theory, which creates infinite numbers of pocket universes with different properties. Each of these universes may have different physical laws and constants. Brane multiverse, based on string theory, suggests existence of parallel branes in higher dimensions, each representing a separate universe. Quantum multiverse is based on quantum mechanics' many worlds interpretation, where each quantum choice creates parallel realities. Even more radical is the holographic principle, which may completely change our understanding of space nature. The holographic principle suggests that all information about three-dimensional space volume can be encoded on its two-dimensional boundary. This is a radically new view of space and information nature that may lead to reconsidering our cosmology and fundamental physics understanding. In cosmological context, the holographic principle may explain dark energy as manifestation of information constraints on cosmological horizons. This idea suggests that observed universe properties may be consequences of deeper information principles, not just physical laws. As observational data accumulates, increasingly bold alternatives to traditional dark matter and dark energy concepts emerge. Recent research proposes radical alternatives to dark matter and dark energy concepts. Some theories claim these mysterious components may be illusions arising from incomplete understanding of gravity or other fundamental forces. Interacting dark energy models suggest that dark energy and dark matter are not independent components, but interact with each other in complex ways. This may explain some observational anomalies and the coincidence problem, why dark matter and dark energy densities have comparable values precisely in our epoch. Such models represent attempts to create a more unified picture of cosmological evolution. Gravitational wave astronomy development opened new possibilities for testing alternative theories. Recently proposed models suggest that gravitational waves, not inflation's scalar fields, could have been the main mechanism for generating primordial density perturbations. These models claim that quantum fluctuations of the gravitational field itself are sufficient to explain observed cosmic microwave radiation properties. Such approaches may radically change our early universe understanding and offer new observational tests through studying primordial gravitational waves. Future gravitational wave detectors may become decisive tools for distinguishing between alternative cosmological theories. Alternative theories' value is ultimately determined by their capacity for experimental verification. Observational technique development opens new possibilities for testing alternative cosmological theories. Gravitational wave detectors like LIGO and Virgo may detect primordial gravitational waves from inflation or other early universe processes. Future space missions, including dark energy study satellites and next-generation telescopes, will provide data that may decisively distinguish between different cosmological models. These observations include precision measurements of universe expansion, studying structure formation at various scales, and searching for deviations from standard model predictions. Alternative cosmological theories raise deep philosophical questions extending beyond pure physics. Alternative cosmological theories raise deep questions about scientific knowledge nature and observational testing boundaries. Some of these theories, especially those related to multiverse, touch on questions about what constitutes scientific theory if it's fundamentally untestable. The multiverse concept, for example, may explain nature constants fine-tuning, but may be fundamentally unobservable. This raises questions about where the boundary between science and philosophy lies, and what criteria should be used for evaluating scientific theories. Nevertheless, alternative approaches development plays a vital role in science, forcing researchers to critically reconsider fundamental assumptions and seek new ways of understanding the universe. Even if many of these theories prove incorrect, they stimulate development of new ideas and methods that ultimately lead to deeper cosmic understanding. Science history shows that today's alternative theories may become tomorrow's revolutions in our reality understanding. Modern mysteries and open questions. As cosmology achieved greater successes in understanding large-scale structure and universe evolution, paradoxically, the number of fundamental questions did not decrease but grew. Modern cosmology, despite its impressive achievements, faces a number of fundamental mysteries that may require revolutionary reconsideration of our universe understanding. These open questions not only indicate modern knowledge boundaries, but also determine future research directions, showing that even in the era of precision cosmology, the universe continues to guard its deepest secrets. Perhaps the most fundamental of modern cosmological mysteries is dark matter's nature, a substance that comprises the material universe's foundation but remains completely elusive. Dark matter remains one of modern physics' greatest mysteries. Comprising about 27% of all mass energy in the universe, it exceeds ordinary matter by 5 times in quantity, but practically doesn't interact with electromagnetic radiation. Dark matter discovery history began with astronomical observations that showed discrepancy between observed matter and gravitational effects. Dark matter existence was postulated to explain observed galaxy rotation curves, gravitational lensing, and large-scale structure formation. Without dark matter, galaxies would rotate too fast and fly apart. Stars in galaxy outer regions move at velocities requiring much more gravitating mass than can be explained by visible stars and gas. But despite dark matter's decisive role in cosmology, its microscopic nature remains completely mysterious. Despite decades of intensive searches, no dark matter particle has been detected in laboratory experiments. Main candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but none has received experimental confirmation. This situation creates a paradox. We know dark matter must exist from cosmological observations, but cannot find it in the laboratory. Facing this problem, some researchers propose a radical alternative. Perhaps dark matter doesn't exist at all, and observed effects are explained by modified gravity laws at large scales. Recent work shows that changing fundamental constants over time may mimic dark matter effects. If these alternatives prove correct, this would require complete reconsideration of our fundamental physics understanding. If dark matter presents a mystery, then dark energy is a true cosmological puzzle. Even more mysterious is dark energy, comprising about 68% of the universe and responsible for accelerated cosmic expansion. Discovery of cosmological acceleration in 1998 became one of astronomy history's most unexpected results, since intuitively gravity was expected to slow universe expansion. Dark energy's nature remains one of modern physics' greatest mysteries. The simplest dark energy explanation is Einstein's cosmological constant, representing vacuum energy. However, here arises a problem that can be called theoretical physics' greatest failure. Theoretical estimates of quantum vacuum energy exceed observed dark energy value by 10 to the times. This is the largest discrepancy between theory and observations in physics history. This discrepancy is so vast, it's difficult even to imagine. If vacuum energy actually had theory's predicted value, the universe would expand so rapidly that atoms couldn't hold together. The fact that we exist means something is fundamentally wrong in our vacuum or gravity understanding. The search for alternative explanations led to various dynamic dark energy models' development. Alternative models include quintessence, a dynamic scalar field whose energy density changes with time. Recent DESI experiment data hint that dark energy may indeed be variable, requiring standard cosmology model reconsideration. If confirmed, this would mean the universe not only accelerates, but that acceleration itself changes unpredictably. Expanding universe creates fundamental problems for understanding information and causality. Finite light speed creates fundamental limitations on causally connected region sizes in the universe. Cosmological horizon determines maximum distance light could have traveled since the Big Bang. This creates paradoxes questioning our physical laws' understanding. The most famous of these paradoxes is the horizon problem. Observations show that cosmic microwave radiation regions that were never in causal contact have practically identical temperatures. How did they agree to have identical properties? This horizon problem is partially solved by inflation theory, but raises deep questions about information and causality nature in cosmology. A related and even deeper question concerns information fate in expanding universe. If expansion accelerates, then in the distant future, most information about the modern universe will become fundamentally inaccessible to observers. This raises fundamental questions about reality nature. If information becomes inaccessible, does it cease to exist? One of modern cosmology's most philosophically troubling aspects is the fine-tuning problem. Standard cosmology model requires incredibly precise fine-tuning of initial conditions. Universe density should have been very close to critical. Deviations from homogeneity should have been small but not zero, and space curvature should have been practically zero. Slightest deviations from these values would have led to a completely different universe. The problem is aggravated by inflation, which explains some of these coincidences, itself requiring specific initial conditions for the inflaton field. Moreover, most inflation models lead to eternal inflation and multiverse, where our universe is just one of infinite multitude. This solves fine-tuning problems statistically, but at the cost of introducing fundamentally unobservable entities. Even more troubling is fundamental nature constants fine-tuning problem. Fundamental nature constants appear very precisely tuned for complex structures and life existence. Small changes in elementary particle masses, interaction strengths, or cosmological parameters could have made the universe incapable of forming stars, planets, or biological structures. For example, if strong nuclear interaction were slightly weaker, nuclei heavier than hydrogen couldn't form. If slightly stronger, all hydrogen would convert to helium. At the root of many cosmological problems lies the absence of complete quantum gravity theory. Unifying quantum mechanics and general relativity remains theoretical physics' unachieved goal. This unification is necessary for understanding Big Bang's earliest moments and black hole nature. Without such theory, we cannot fully understand Planck epoch or solve cosmological singularity problems. Main quantum gravity approaches, string theory and loop quantum gravity, offer radically different pictures of space-time at Planck scales. String theory assumes extra dimensions and fundamental objects sized at Planck length, while loop quantum gravity proposes discrete space-time structure. So far, neither approach has led to final theory capable of making testable predictions. Quantum gravity problem is closely connected with an even more fundamental mystery: time's nature. Time's nature in cosmological context remains deep mystery. In relativity theory, time is relative, but cosmology apparently requires some cosmic time to describe universe evolution as a whole. This creates conceptual problem. How can universal time exist in relativistic theory? Moreover, the question remains open whether time existed before Big Bang or time itself arose together with space. Some theories suggest time may be emergent property of more fundamental reality. If so, our ordinary cause and effect concepts may be inapplicable at cosmological scales. Another fundamental mystery is matter's predominance over antimatter in the universe. Matter dominates in the universe, not antimatter, although elementary particle physics laws predict equal matter and antimatter production in early universe. Explaining this asymmetry requires violating some fundamental symmetries. Sakharov conditions for generating baryon asymmetry include baryon number violation, C and CP symmetry violation, and deviation from thermodynamic equilibrium. Although particle standard model includes some of these processes, they're insufficient to explain observed asymmetry. This means either new physics exists beyond standard model or our early universe understanding is incomplete. Among cosmological mysteries is one that seems technical but may indicate fundamental problems in our understanding. Observed lithium-7 content in old stars is approximately 3 times less than predicted by primordial nucleosynthesis theory. This lithium problem has remained unsolved for over 20 years and may indicate incompleteness in our understanding of either nucleosynthesis or stellar evolution. Possible explanations include lithium destruction in stars, exotic particle existence in early universe, or errors in nuclear data. However, none of these explanations has received definitive confirmation. This problem shows that even well-understood cosmology aspects may hide unexpected complexities. One of modern cosmology's most intriguing mysteries is the so-called coincidence problem. Why do dark matter and dark energy densities have comparable values precisely in our cosmological epoch? In the past, dark matter dominated. In the future, dark energy will dominate. But now their contributions are comparable. The probability of living precisely in this unique epoch seems suspiciously low. This coincidence may be anthropic effect. Structures necessary for observer existence may form only in epochs when these densities are comparable. Alternatively, this may indicate fundamental connection between dark matter and dark energy. Some theories suggest these components aren't independent but represent different aspects of unified phenomenon. As observational capabilities improve, new mysteries arise that may require established theory reconsideration. Modern high-precision observations reveal new anomalies that may require standard model reconsideration. Hubble problem became one of modern cosmology's most discussed problems. Different methods of measuring Hubble constant give incompatible results. Local measurements give values around 73 kilometers per second per megaparsec, while cosmic microwave radiation-based measurements give around 67 kilometers per second per megaparsec. This difference may seem small, but it's statistically significant and may indicate new physics. Large-scale structure anomalies represent another problem type. Observations show less matter clustering than standard model predicts. This may indicate problems with our dark matter or dark energy understanding. Unexpectedly bright early galaxies discovered by James Webb Space Telescope show that structure formation in early universe occurred faster and more efficiently than expected. Some of these galaxies are so massive and bright for their age that they question star formation models and black hole growth in early universe. Despite numerous unresolved problems, cosmology's future looks promising thanks to new observational and theoretical methods development. Solving these fundamental problems will require combining new theoretical approaches and revolutionary observational data. Future dark matter search experiments, next-generation gravitational wave detectors, and new space telescopes may provide key clues. Gravitational wave astronomy opens completely new universe information channel, allowing study of processes inaccessible to electromagnetic observations. Future detectors may discover primordial gravitational waves from inflation, providing direct information about earliest universe processes. perhaps most important, is quantum gravity theory development, which may radically change our understanding of space, time, and matter. Such theory may unify all fundamental interactions and explain observed universe properties based on deeper principles. Physics history shows that revolutionary theories often solve multiple problems simultaneously, offering unexpected connections between apparently unrelated phenomena. In conclusion, it's important to note that modern cosmology is in a unique position. On one hand, we've achieved incredible precision in describing large-scale structure and universe evolution. On the other hand, this precision has revealed fundamental problems that may require revolutionary reconsideration of our basic reality concepts. Modern cosmology stands on the threshold of new discoveries that may be as revolutionary as discovering universe expansion or cosmic microwave radiation. These mysteries remind us that even in the era of precision cosmology, the universe continues to guard its deepest secrets. But it's precisely these unresolved problems that make cosmology one of modern science's most dynamic and exciting fields, promising that coming decades will bring discoveries that may radically change our cosmic understanding and our place within it.